let's talk about the math policy. This is my second time. If you had the lab 1 with me, we talked about this policy. And this is not my policy, this is university's policy, right? And we have to follow the university's policy, right? I don't really care if you want to debate the science. I'm not a health scientist. I don't know anything about this. I don't have any opinion. This is a rule. You have to follow, okay? Is this understandable? This is not my rule. Okay. And as far as the labs go, I will talk to your TA. Thank you for bringing this up. And this is actually very important because your main instructor in the lab courses is your TA. I used to go to the labs myself. Then we had like 4 students, right? With 30 students and 3 sections, I can't really go to the labs, right? So you have to bring up the issues with the lab, right? And all of you, in one way or another, have that course with me, right? Or are going to take the course with me, right? Either lab 1 or lab 2. Next semester. There are 2 students who are going to take it next semester, right? 2 or 3 students, yeah. Next year, actually. We don't really offer it every semester. Not yet. Okay. So, let's begin. We covered chapter 1 of the Propulsion book. In the previous lecture, you already have access to the homework. That's essentially the homework problems of the chapter. I've given you all of those problems to work with. I think they're pretty easy to handle problems. You have to be a little bit creative to work on those problems, but if you have a question, please make sure to ask those questions. If not, let's move on. So in this chapter, which is the chapter 2, we are going to review the basics again a little bit, just for like 10-15 minutes. Then from this, we are going to graduate to talk about the fluid flow that is related to the propulsion. So propulsion focused fluid flow, if you will. Well, what are the specifics of fluid flow when it comes to propulsion? Like, what are the differences, or what are the things that we need to consider when we are talking about the fluid dynamics of propulsion? The first thing you need to take into account is the fact that this is a flow inside a duct. Right? It is always the case when it comes to propulsion. We are dealing with flow inside the duct. And if you recall from your aerodynamics, we have different flow regimes. And we have different parameters we use to distinguish these flow regimes. For example, Reynolds number is going to tell us whether a flow is laminar or turbulent, right? Do we remember this? Laminar versus turbulent. Do we remember the Reynolds number? The cutoff Reynolds number for the transition from laminar flow to turbulent inside a pipe?
2 million?
No, not 2 million. That is for the transition from laminar to turbulent on a flat plate. So essentially on a wing, right? Which is for your external aerodynamics that you have dealt with in your aerodynamics course, right? Internal aerodynamics, which is propulsion fluid flow.
I don't think we did internal.
You haven't studied this, right? That was the answer I was looking for. So the transition here in a regular duct flow happens at Reynolds number of 2300. But the flow inside the propulsion chamber, inside the jet engine, is so complex that we don't really deal with laminar flow analysis, turbulent flow analysis. We usually look at it from a system level perspective. So you calculate the enthalpy at each state, thermodynamics analysis essentially, right? We don't really deal with this Reynolds number that much, right? So we are mostly concerned with the thermodynamics of the flow. Thermodynamics of the flow. Right? So essentially we want to find the enthalpy at each state, or entropy at each state. One question I have for you is, that's actually when it comes to the, if you want to go back to the flow regimes, can we consider this flow incompressible? To answer this question, what you need to do, what you need to know is, you need to know what incompressible flow is. What are the specifics of incompressible? So what does it mean for a flow to be incompressible?
That Mach number less than 0.3.
That's a cutoff number. But what happens to the flow when Mach number is less than 0.3, right?
The specific volume remains unchanged.
A specific volume remains unchanged. We usually talk about this in terms of density, right? So density remains unchanged. And we usually neglect frictional losses, right? Specifically when you are neglecting frictional losses and a lot of other type of losses, meaning that you are neglecting viscosity specifically, we are dealing with another type of flow which is called inviscid flow. That's the most basic type of flow that we can deal with, right? So take a look at these two, neglecting frictional losses and also a constant density. Is this something we can claim when it comes to propulsion?
No,
No, why not?
because for a lot of our thermal processes, there's a change in specific volume.
We have chemical reactions happening, right? We have combustion happening, compression. A lot of things that are happening are directly related to changes in a specific volume and density, right? So our flow here is definitely not incompressible. That's for sure. Or it is definitely compressible, right? So one of the factors we have to deal with is compressibility of the flow. Right? But what about the frictional losses? Can we neglect those frictional losses? And can we assume those don't really exist? Let me actually back up a little bit. Do you understand what these frictional losses are? What is this referring to?
Just like shear forces across surfaces.
Shear forces, that's exactly what it is. So when you have flow near a wall, you are going to have, you are going to lose momentum to the wall. But that's the idea. Okay. With flow around the wings, especially low speed aerodynamics, we can safely assume that there is no shear loss, right? There is no frictional losses. Can we make the same assumption in a propulsion analysis?
I'd say no, right?
Why not?
Is it much faster?
Much faster. So we have Nicholas is saying that because the flow is faster, we cannot neglect frictional losses.
I don't think we can neglect it because of the compression in it. It's kind of like when you go faster with the wing, the compressed air heats up outside of it because it's.
That's a different type of heats up what?
But when the compressed air in the duct quality, you can't neglect friction because there's more in the space.
There is more air inside. That's what
I
you're
just think
saying?
due to compression, that's why you can't.
Okay.
neglect the friction.
Okay.
Can
Okay.
we neglect it and just have that be part of like our efficiency?
That's what we are going to do eventually, yeah. But I mean, in reality, can we neglect this?
That's what I was gonna say. I was like, isn't it just relative though? Because We're only looking at our inputs and outputs.
We are eventually we are only going to look at this as the efficiency part, right? All of the losses is going to be combined inside the efficiency, but the flow itself cannot be assumed to be implicit flow, mainly because of whatever you guys actually mentioned, and there's a flow inside a small duct, right? So the boundary layers that are forming are going to have a very huge impact on the flow. It is not like flow around the wing that you have this big of a boundary layer, right? And you have the flow around it, right? A huge flow around it that is not affected by the boundary layer, okay? So it is very important for us to understand that this frictional losses are going to be very important inside in propulsion. So all of these, the compressibility, the frictional losses, compressibility, I don't know if I'm spelling this correctly, the non-inviscid nature of the flow, all of this is going to contribute to and also if you're dealing with higher speeds, is going to contribute to the generation of shock waves, formation of shock waves, which is something we are going to discuss in this chapter of the book. Okay. But again, we always start with the ideal gas law. We always assume that the air inside your propulsion system is an ideal gas, and we have the ideal gas law relationships for it. This is your pressure, just a reminder, density, gas constant, and temperature of the system. This gas constant, we have a universal gas constant that is 8,314 kilojoules per kilomole Kelvin, I'm sorry. But when you are dealing with air, this gas constant is going to be divided by molecular weights to give you, I'm not sure about this number, but it should be around 287 joules per kilograms Kelvin here. In the British system, your universal gas constant is going to be 4.97 10 to the 4 foot-pound force slugs mole degrees Rankine. And we just went over this, I think, a couple of weeks ago for an ideal gas law. The changes in enthalpy can be related to the changes in temperature, but this is with the assumption that the heat capacity does not change with temperature, right? Cold air standard, that was the standard use. So what can we say about the changes in internal energy? How does it relate to temperature? Changes in temperature, does anyone remember? Again, this is constant pressure heat capacity. CVDT, exactly. So internal energy is related to constant volume. Heat capacity multiplied by changes in temperature. Well, we already know that Cp and Cv are very much a function of temperature. But this assumption is only true for a small ranges of temperature. This is a very important thing to consider. Okay. We have the first law of thermodynamics that tells you the changes in heat of the system. Just a rearrangement of the first law is going to be equal to the changes in internal energy plus changes in work. What is the difference between this delta and this D? Both of them are referring to a small change in something. Right?
Partial versus full.
What's that?
Partial versus full.
That's a partial is like this, right? This is a delta. This is a delta compared to a round. This is a round.
A what?
A round. That's the Greek letter round. But delta is different from partial. This.
So like delta would be changed from like stop and or start and end, whereas the D is the change throughout that process.
You are actually, it is the other way around. So this delta is referring to a change that is path dependent. Which essentially means that changes of heat in heat and work are path dependent. But changes in internal energy essentially is going to be the internal energy at state 2 minus the internal energy at state 1, right? Does this make sense? Just a reminder. What will happen to this first law of thermodynamics in a closed cycle? All over the cycle.
It's equal to conserve
What is conserved?
energy.
Energy. So what will happen to this equation then?
The left side equal to 0.
No.
Delta Q equals delta W.
Delta Q is going to be equal to delta W, right? So the changes in internal energy is going to be 0 because we are going back to the same state, right? And that actually tells you that is an interesting example actually of that is going to demonstrate the fact that Q and W are path dependent, right? Although DE is 0 because we are at the same state, but Q and W are not 0, right? Because we have gone through a path to get to that location. Changes in internal energy went back to 0, but there have been some heat transfer and also work done by the system or on the system. Second law of thermodynamics. Who can tell me what was the second law of thermodynamics?
Entropy always increases.
Entropy always increases, which is true. Okay, can you give it to me as an equation, like a Clausius inequality? Does anyone remember this? Inequality. This told us the TDS is always larger than the amount of heat transferred from one state to another state, right? Temperature multiplied by the dS. Larger is equal or, which is talks about the fact that the entropy is always increasing in a process. Do you remember all of this, or do we have any questions about all of these parts? Because this is all some things that we went over, I guess, a month ago, right? Right? Do we all remember this, or do you want me to continue the reminder, the review? Yes.
I'm a little confused on how flow over a wing is inviscid and flow through a pipe is not.
The flow is never inviscid. You can assume a flow is inviscid because of lower amount of error that is present, right? Does it make sense? We don't really have any inviscid incompressible flow. It is not. We don't really have it. Okay? Any other questions? The two equations I really want you to take away from this review is the relationship between Cp and R, which is gamma over gamma minus 1 multiplied by R, and Cv is 1 over 1 minus gamma multiplied by R. Again, we are dealing with all of this for air. So for air, we usually assume gamma is 1.4. Right? But let's say you don't have the Cp, you don't have the R, and you don't have the Cv of a specific gas, of a specific molecule. How would you go about calculating the ratio of a specific heats? Is there any way? Let's say just this, they tell you that we have this molecule which has this formula, right? It has 2 atoms, whatever, right? Is there any way for us to calculate the ratio of a specific heats? Does anybody remember? I mean, we went over this in our high school chemistry. I don't know if you guys go over this in your chemistry in high school. That's why I'm asking. If you don't know, it's all right. The reason I'm asking is this. Okay. So there's something called the degree of freedom, right? That depends on the number of atoms and how freely your molecule can move, right? Molecules have different types of movement. It's either a rotational movement, they rotate around themselves, around an axis, right? Or there's a vibration in place, they vibrate in place, or they move, right? Depending on the type of bond they have with other molecules and atoms inside the molecule, right? These movements can be limited, right? If you are dealing with a solid, molecules can only vibrate in place, right? They can't really translate or rotate, right? That's the idea here. So this degree of freedom is going to change. So we have this for air as well. And for air, we have the degree of freedom is 3 because it can do, it's a gas molecule, it can do whatever it wants to do. We are going to have 5 by 3. And this is going to be not for air, it's specifically for oxygen. It's going to be 5 by 3 or 1.6. But for air is going to be different and is going to be 1.4, as you all know. Let's wrap up the review by just remind you guys of the relationship, the isentropic relationships. First question I have for you is, what is an isentropic process? I've asked this 10 times now, right? And because it's very important. Yes?
Constant entropy.
Constant entropy. What is a constant entropy? What do we call a constant entropy process?
Well, like specifically what kind of cycle?
What is the type of, what is the name of that specific process?
Oh.
So let me rephrase the question. Rephrase the question. What will happen to your process if the entropy doesn't change? What is the specific thing that only applies to those processes, those specific processes?
It's reversible.
It is reversible. You can reverse it. So
Adiabatic. No.
reversible, right? Reversible. So constant entropy processes are called reversible. But if we already have a name for constant entropy processes, what is the difference between an isentropic process and a reversible process? Okay, let's actually do this. Let's do a quiz on this. I want everyone to jump in, and then you submit the quiz. What is the definition of an isentropic process? Give me the names, give me the specific things that is important in an isentropic process. And you have 2 minutes, I guess. You really don't need more than 2 minutes. Okay, your 2 minutes is up. This is what we're gonna do. We're gonna start from Drew, right? We're gonna start from Drew. You're gonna read through your answer, right? And stop writing. And I'm going to give you your attendance right now in front of me. I'm just gonna give the attendance to you. Okay, let me just bring this up. Let's start with Drew. Okay, say. Let's start with Drew. What was your last name, Drew?
Standard.
Drew Sanders. Okay. Present. What's the answer?
So, like, it's constant entropy, but I guess the difference is, like, isentropic is just when heat is transferred into work or vice versa. Like,
Heat is transferred into work,
like in a turbine.
like in a
There's
turbine.
like heat energy to work.
Okay. So your energy is transferred into work. Is that what you're saying? Okay. Not heat specifically. The energy of the system. Okay. What was your name again?
John
John. What's the last name, John?
Hill.
Hill? Okay. John Hill. Present.
Have an isentropic process is reversible, meaning delta S equals 0.
And that's it? Okay. Let's go with Igor.
I have a delta S equals 0. It's reversible, so there's no friction loss, and adiabatic, so no heat transfer.
Okay. Adiabatic, no heat transfer. Okay. Kerem?
So,
What's the last name, Kerem?
taking.
Okay.
So, I don't have much, but I said we can go back to the same condition that we started, since it's adiabatic and reversible.
Same state that adiabatic and reversible. Okay, so that's what the answer. It is adiabatic and reversible. Okay. Trey?
I have delta S equals 0 and adiabatic.
Delta 0, adiabatic. Emery?
That same thing.
That's the same thing. Okay, adiabatic, reversible. Lawson?
Constant entropy S, or constant entropy variable S, and adiabatic, so no heat transfer.
Adiabatic, so no heat transfer. Lawson. Let me find. What's your name? What was your name?
Camden Whitehead.
Camden, yeah. Camden. What was the last name, Camden?
Whitehead.
Whitehead. Okay, what's your answer?
As you said, constant entropy becomes reversible and is adiabatic.
Adiabatic.
I have reversible adiabatic constant entropy, so S1 equals S2.
Did you have adiabatic as well? Okay. Your name was
Thomas Murphy
Thomas Murphy.
said it was reversible, and it was like volume and pressure relationships. Like it's like the same.
But that's the volume and pressure relationship is something you conclude from the conditions, right?
Yeah.
That's not a condition of the
No.
process itself. So just the reversible then, okay? Zach, right?
Yes. I just had that there was no heat transfer because it's adiabatic and the delta S because it's reversible.
Adiabatic, okay. Joseph, right?
Yes, sir. I had that it was reversible, so the entropies of the two states are equal. Well, and then I had the heat transfer 0, but I mislabeled it as isotropic instead of adiabatic.
Okay. Yeah, okay. Nicholas?
Entropy change is 0, so delta S is 0. And then I said no heat enters.
No heat transfer?
No heat transfer is what I meant.
What was the first thing you
I
said?
said no heat enters.
No heat enters. Okay. Okay. Yeah. So most of you are actually correct. And again, the reason I'm stopping here is because I want to make sure that we are clear on this one. Isentropic relationship is the backbone of all of our analysis in propulsion, right? Isentropic process. Isentropic process is reversible, as all of you mentioned, meaning that the entropy change is 0, and the significance of that change, that 0 entropy change, is that we can actually we can move the other way around in the process. We can go from a state 2 to a state 1. That's what it means. Which there is no reversal process anywhere in the world, right? That's an ideal process that doesn't happen, right? Anywhere, right? And the second part of an isentropic process is that it is adiabatic. What does adiabatic mean? The heat transfer is 0, right? So you can actually, your system can do work on the environment. You can actually do work on the system, but there is no heat transfer to the system. So the turbine you mentioned, we don't really have any heat transfer in the turbine, right? We are not heating up. We are not removing any heat from it, right? There is no heat exchange. We are not cooling it down, right? The reason it is being cooled down is because of the work that is being extracted. It's because of the expansion, right? So there is no heat transfer there. Just keep that in mind. Again, isentropic process, adiabatic, reversible. Sometimes I use adiabatic reversible instead of isentropic. And you have to understand this. This is a very important this is a very basic part of propulsion. So if you graduate from this course and get a D, let's say you just passed the course, and you go to another course and they ask you what is an isentropic process, and you fail to say it's a reversible adiabatic, your future instructor is going to come to me and say you had to fail this student because they don't know what the isentropic process is, right? This is the backbone of propulsion. I want you to understand this. So what were the processes? What were the pressure relationships that, what was your name again? Thomas. I keep forgetting your name. That Thomas mentioned. We had the pressure ratio between a state 1 and a state 2, which is equals to temperature ratios to the power Cp divided by R. If you recall, we actually got this relationship from the main entropy relationship we had, right? You remember that the Cp natural log of temperatures minus R natural log of whatever, right? That's equals to 0. And if you go back to this equation here, you can see Cp divided by R is actually gamma divided by gamma minus 1, right? We can have a similar relationship for densities to the power gamma, or we can actually write this in terms of a specific volume, which is going to mean that it's going to be to the power, to the power gamma, or V2 divided by V1 to the power minus gamma, right? So it can be in terms of a specific volume or density. Most important relationships that you should know are these two, the isentropic relationship between the pressure and temperature of the two states, right? Other than that, you can either use the ideal gas law, or these are the most important thermodynamic relationships, or not most important, most useful thermodynamic relationships that you should be aware of, right? But there are a couple of other relationships that we need to be familiar with, and these relationships goes back to the basic principles of fluid mechanics or aerodynamics in general. We have three main principles there. The first one is conservation of mass, right? Second one is the momentum equation, which is derived from the Newton's second law. So conservation of, I don't want to call it conservation, let's just call it momentum equation. And the third one is the energy equation, which is derived from the energy balance in the system. Who can tell me what was the conservation of mass equation in aerodynamics? When did you have your aerodynamics course?
2 years ago.
2 years ago. Who had aerodynamics last year? You haven't had aerodynamics yet? Not yet?
No.
Okay, that's not good. Mhm.
I can give it a shot.
Yeah, whoever can give it a shot. Conservation of mass equation.
M dot 1 V1 equals M dot 2 V2.
Okay, m dot v. What is that? What does that parameter represent? M dot v.
Mass flow rate volume.
That's m dot multiplied by velocity,
Yeah, I'm sorry, wrong.
right?
Yeah.
No, I'm asking. Is that
Yes.
okay? What does it represent? Does it represent any form of mass flow rate?
I think so, yes. If it's M dot, yeah, it's change of mass.
But you're multiplying that m dot by something else, right?
You have to add area to that.
So you are saying m dot multiplied by velocity multiplied by area, and that's conservation of mass
1 equals 2.
equals
It's
to.
like n equals L.
Okay. You're making it a little more complicated than it is for yourself. We're talking about conservation of mass. What does it mean? Mass 1 equals to mass 2. So m dot 1 or m dot in is equals to m dot out. That's it. There's nothing else to it. How do we calculate m dot? That we can actually use density, area, and velocity, right? Just keep that in mind that we are finding these equations for a steady state condition. So there is no transient changes. There is no change with respect to time. Right? If there was a change with respect to time, then your equations would have been a little more complicated. You should have actually included d dt of m as well, which would have been equal to m dot minus m dot in minus m dot out. But this is 0, so okay. So this is your main equation. between in, density in, area in, velocity in is equals to density out, area out, and velocity out. In our analysis, we are going to assume that the flow here is a one-dimensional, a steady flow. Or let's actually call it, your book calls it quasi, because it's not a real one-dimensional, but there is no real one-dimensional flow anywhere, so that quasi is not necessary.
Quasi-linear?
What's that?
Like quasi-linear?
It is quasi one-dimensional, so like similar to one-dimensional, right? Right? So what does it mean? What does a one-dimensional flow mean for this equation?
Velocity only changes in respect to x.
Velocity only changes.
The x direction.
There is that you are actually getting wrong. This essentially means that there is only movement in the x direction, right? So there is no movement in the other direction. There is no velocity. Doesn't mean that we don't have a three-dimensional system. We have a three-dimensional system, but at every cross section, all of them are moving at the same velocity, right? So this v, if you recall, I don't know if you know this, velocity vector is ui in a Cartesian coordinate system is ui vj. That's the component of velocity in the x direction. J is the component, v is the component of velocity in the y direction, and plus wk, component of velocity in the z direction. So if you are talking about the Cartesian coordinate system, and if you're dealing with one-dimensional flow, this is the only component that is present there. So your equation is going to be rho in, a in, u in is equals to rho out, a out, u out. This is a conservation of mass. So mass is conserved. For a steady state, one-dimensional, actually inviscid flow. We are assuming the inviscid. We are making the assumption that it is inviscid as well.
And laminar.
What's that?
And laminar. If it's turbulent, wouldn't it be going in multi directions?
You can actually, that's a very good thing you brought up. We don't really cover turbulence at all in undergraduate anywhere in the world, unless you take a specific course on turbulence, right? But what you can do is that you can apply this equation to turbulent flow as well, as long as you are taking an average of velocity, right? You can use the velocity average there. You can apply this equation. But we don't really deal with the turbulent flow analysis. So if you were to analyze the turbulent flow, you will probably given an average velocity that you have to deal with. But I don't see how you will. Okay, so conservation of mass. Let's talk about the momentum equation. I'm pretty sure you remember that the momentum equation comes from the Newton's second law. What was it, because I just said it, right? That's why you remember. What was the Newton's second law?
F equals ma.
F equals m. That's sigma F equals to m a, right? But we don't really, for our purposes, we don't really use a. We use the derivative of velocity with respect to time, right? And since your mass actually may change, right, we haven't made any assumptions yet, we have to take this inside the integral as well, right? Inside the derivative. So sigma f is equal to d mv dt. Okay. What is this parameter? M multiplied by v. Momentum, right? That's why I asked when you said m dot v, that's why I was pressing you on it, because this is not actually mass. This is not related to mass. This is momentum, right? So this equation is actually your momentum equation. And to simplify this, we can actually say net force in a direction is going to be equals to m dot, that dm dt is going to be represented in m dot, right? U in minus m dot u out. Actually out minus in. I'm sorry. Momentum equation, conservation of mass, and the last thing we need to deal with is the energy equation, or conservation of energy. Energy equation itself is usually it requires an extensive discussion. So what I'm going to do here, instead of going through the proof of it, we can actually use the Reynolds transport theorem to prove this. Have you ever heard this term, Reynolds transport theorem? No? Not at all. Okay, let me write it down with you. Do you know about the intensive and extensive properties? Yes. What is an intensive property? What is an extensive property? Did we talk about this in this class? Okay, we did. Okay, if we did, then you have to be able to answer this question. What is an intensive property? What is an extensive property?
Intensive, something that's, is it independent of mass?
The extent depends on the size of the intensity.
Extensive depends on the size.
Or it's dependent on it, and the intensive is regardless of how, like, the size of the system.
So, okay.
Or it depends on mass.
It is, he is actually in the correct direction. So your extensive property is, for example, is going to be your volume. Your intensity property, let's actually do energy. Energy, your intensive property is going to be energy divided by mass. Let's actually call them just a regular property, B, and intensive, let's call this a small b. Reynolds transport theorem, it is this equation. And the reason I'm doing this is because later on, if someone asks you, you can at least say, I've seen this, right? The derivative of this extensive property with respect to time is going to be equal to the integral partial time of integral of rho b, I'm sorry, there's density of the whatever fluid you have multiplied by the intensive property, and you want to take the integral over the volume plus rho b. I will explain these in a second. This is a very complicated formula. Yes.
Is the second integral also with the partial t, or no?
This?
Yeah.
Partial t, yes.
And the second integral is also.
No. That
Oh, okay.
second integral is not.
Wait, that's density, right? Not,
What's that?
that's density. P is density.
Yeah.
Rho is density. This is not P. This is rho. Yeah.
Oh.
This is a very simple equation, right? See, I gave you the equation before the proof, so hopefully this one works better for you. This is a very, very complicated equation, but represents a very simple concept. Changes of a property inside the control volume is going to be equal to the changes of the generation or destruction of that property inside this volume, right? And how much of that property has left or has entered this control volume. Very simple. Does this make sense? the changes of something inside the control volume is equals to generation or destruction of it, plus whatever has moved out or moved in from the valves. Pretty simple, right? Like if you have how many, yes?
For the second half of the equation, it's rho times the
The
property.
intensive property.
Velocity, and what's that next?
Okay, that's the normal. Velocity normal to a surface. See, if this is your surface, you are talking about the velocity normal to the surface. That's velocity dot n, no, and dA. Okay, let me try to explain it a little better so you can understand it. You are sitting in class, right? Changes of number of students, number of people in the class over time is going to be equal to changes, the generation or destruction of people in class. I assume we cannot generate any people here because as far as I can tell, we don't really have any ovaries in this class, right? But we can kill each other, so we can we can do the destruction, right? So that is going to be the changes of us, number of people inside this class, is going to be equal to whether we kill anyone or not, plus whether someone moves out of this door or comes into the class, right? Does it make sense? So this whole equation, the Reynolds transport theorem, represents this. And all of the equations in fluid mechanics, aerodynamics, can be derived from this. Simple, very simple equation. See? It just changed. So the number of people changed. Yes?
This doesn't have anything to do with Reynolds number? Is this just because he made it, or?
It doesn't have anything to do with Reynolds number, no?
I just heard like Reynolds transport theorem.
It is the same. It is the same Reynolds, yeah, but it's a different.
Is it Ryan Reynolds?
No. I wish, but no. Yes.
Is that a unit vector next to the V in the second?
This is a normal vector, yeah. Unit normal vector, exactly. Which essentially refers to that this movement out of a surface has to be normal to that surface, right? Is normal to that. So all of these conservation equations we can derive from this. We are not going to go over derivations. The only thing that I'm going to give you is the final. Let's actually do the final energy equation. Let's assume there is no, there is uniform flow. Uniform flow. What can you say about the energy equation in the system? And this energy is essentially energy transfer equation. So that energy transfer is not going to be due to the fluctuations in the flow, right? What are the types of energy transfer we have seen up until this point?
You mean just like potential to kinetic and kinetic to heat and stuff like that, or?
I guess, yeah, that those would work as well. But that, like, think about first law of thermodynamics. We have two specific types of energy transfer, right? So the destruction and generation of energy in a system can be due to work or heat transfer, right? So this side is going to be replaced by Q dot minus W dot, right? This side of the Reynolds transfer theory. And for this other side, we have already assumed the steady state, no changes in internal energy and whatever, right? So that side is already zero. Changes of internal energy is equals to zero. But this side, if your control volume has an inlet and an outlet, energy actually can come into the system and leave the system. Like, think of a turbine. A very high energy fluid comes into the turbine, then we extract some work out of it, right? And then a lower energy system, a lower energy fluid leaves the turbine, right? So the amount of energy in that fluid is going to be m dot h in minus m dot h. Let me just, yeah. M dot h out. So this refers to the energy that is leaving the system or coming into the system. This refers to the work done on the system by the system, heat transfer to the system or from the system. If there is no shaft work, and if the system is adiabatic, then what will happen to this energy equation?
The right side would be 0, right?
All of the right side?
This would just be Q dot minus W dot.
This no, I'm saying there is no shaft work. What does it mean when I said there is no shaft work? So when you think about it, think about it this way: you have the turbine, your turbine shaft is not moving for whatever reason. That's the shaft work. So does that mean for this equation? W dot is 0. What about the adiabatic? Q is going to be 0. So if there is no shaft work, if there is no work, then m dot h out has to be equal to m dot h in.
Can you relate that to the conservation of mass?
This is the conservation of energy, right?
Just in a different.
It is a conservation by the conservation of a different thing, right?
Okay, yeah.
And eventually, if your m dot is not changing, your enthalpy out has to be equal to enthalpy. This essentially means that if your turbine doesn't rotate, if you remove all of the blades out of the turbine, if shaft doesn't move, your energy coming in, your temperature is not, you're not going to lose any energy. That's the idea, right? Energy is going to be conserved. Unless you have the friction losses, all of those things, which we do have, but we don't really work on. Yes?
This would be a bad thing, right?
Losing.
Well, I mean, if your shaft isn't moving, that's not a good thing. But
Specifically about turbine, yes, it is not a good thing. Yeah, you want your shaft to move, right?
yeah.
But that's specifically about turbine, right? Sometimes you don't really want to lose energy. Let's say think about it this way. Let's say you want to transfer oil from one city to another city, right? And that's usually pressure driven flow. So your energy is due to the pressure difference. The movement is due to the pressure difference, right? If you lose a lot of energy in the system, at some point your flow is going to stop, right? Which is not a good thing. It really depends on the application, right? Okay, what time is it? I guess we stopped a lot here, which is not a bad thing. Let's talk about sound waves. I'm not sure about anything else. Who can define the sound waves for me?
Vibrations across a median, right?
Vibrations.
Median is air, sound wave.
Vibrations across a medium. Vibrations that move. That's what you want to say?
Yeah.
I guess, yes. What do you say?
A compressional wave that travels through a medium.
Pressure waves, right?
Yeah.
Pressure waves. Compression waves don't really mean anything, right? You said compression, right?
Compression. As opposed to longitudinal.
As opposed to
Longitudinal waves.
yeah, I guess so. But pressure waves.
Yeah.
Austin would be proud.
Yeah. Pressure waves. Okay, what else?
They have an amplitude and a frequency.
You are jumping too much into vibration, right? That sound waves are essentially pressure waves, right? And by pressure, when we say pressure wave in propulsion aerodynamics, what we mean simply is that there is a pressure, velocity, and all of the other properties, let's say density, temperature, behind these waves, and after this wave has passed, let's say this is moving in this direction, you are gonna have a different pressure, a different velocity, a different density, and also a different temperature. That's the idea of a pressure wave in fluid mechanics. So what are the specific thing about pressure waves is that they are reversible and adiabatic, the sound waves. What does it mean? It means that the movement of a pressure wave is isentropic, right? And we are specifically talking about sound waves. So, how can we calculate, based on this information that is given to us, how can we calculate the speed of sound? Which essentially means that we want to calculate the speed of this specific pressure wave, right? Yes?
I mean, so in a specific time period, you can get the pressure difference in that specific area. And
Okay.
we can calculate the speed.
How can we calculate the speed from that?
Square root p MRT.
Let's do this. So whenever you wanna, let me ask you this. What is the equation we use for the speed of sound? And that is for Lawson. I'm giving you the equation at the beginning, right? So what is the equation we use to calculate the speed of sound?
Mach.
Square root
A square root of gamma
something t.
RT, exactly. Or we can actually use, we can actually use the ideal gas law to come up with the pressure relationship. It's going to be gamma P divided by rho. Exactly, right? So this is the equation we want to find. How can we find this equation? That's the thing that we want to answer here. We just learned learned about the three fundamental laws, right, in aerodynamics and fluid mechanics. What were those? Conservation of mass, momentum equation, and the conservation of energy. So let's apply the conservation of mass here. Let's say this sound wave is the thing that is fixed, and this air is moving, is passing through the sound wave. We have the sound wave fixed here, air is passing through it. That's the assumption we always have when we do aerodynamic analysis. We assume the aircraft is at zero speed and the air around it is moving, right? Which is a very valid type of analysis. It's not even an assumption, it's just a different type of analysis. Okay, let's apply the conservation of mass. How did we calculate the conservation of mass? Let's say this is your point 1, this is point 2.
Rho n times Vn.
Rho 1, V1, right?
Yep. And would the area be the size of the wave?
Area can be a cross-sectional area, so you can choose that area, right? You have to choose a control volume. That area is an arbitrary area, right? Equals to
Rho 2 V2.
rho 2 V2 A2. What is rho 2 and V2?
Rho 2 and V2.
So rho V, these A's actually cancel out. We're gonna have rho V, then rho plus d rho, V plus dV, right? And if a lot of things will cancel each other out, we're gonna have rho V equals to rho V plus V d rho plus rho dv, I'm sorry, rho dv. Keep in mind these v's are referring to velocities, d rho dv. These two cancel each other out, and we can actually neglect this one. We can take this one out as well. Why is that the case? The last one. Why did I take the last part out?
Product of two small numbers is a very small number.
Exactly. That's a product of two small derivatives, right? It's going to be even a smaller derivative, so that we can actually take it out. We can assume it's zero. Very simple. So your conservation of mass is going to give you, this is a rho, this is not a pressure, is going to give you this equation. What about the momentum equation? What can we get from the momentum equation?
Force balance, or F net.
F net, what are the forces here? It is actually a very important thing that you can understand what is the force that is present here.
The forces of compression.
Forces of compression. What do you mean by that? How can I find the forces of compression?
Pressure times area.
Pressure times area. Pressure forces. Like we call those pressure forces, right? So the force that is present here is actually only the pressure force, right? So for your F net, we are going to have the pressure force, which is going to be PA minus P plus dPA, right? The two forces acting in different directions. This is going to be equal to your m dot v in minus m dot v out, right? What is the m dot v in? That's m dot v1, m dot 1 v1, m dot v out is m dot 2 v2. Okay, so we're gonna get rho u, that's your m dot a, m dot is going to be rho ua multiplied by u plus du minus, I'm sorry, u rho u plus du a multiplied by u plus du. A lot of different phrases.
That's rho UA U.
Yeah, that's m dot u.
Okay.
Okay, that's your momentum.
Can we write just m dot?
No.
Yes, you can, but you eventually have to go back to this because
Okay.
this is the relationship we are going to use here. Eventually, if you do all of the cancellations, this is what you are going to get. Rho u du is equals to the derivative of pressure. This is actually called the Euler's equation. It's one of the most famous equations in aerodynamics and fluid mechanics. And based on this, we can actually find the Bernoulli's equation, right? It's a very fundamental, very basic equation.
I thought Euler's equation was only useful with inviscid flow.
Yes, but this is not Bernoulli's, this is Euler's equation. Based on this, you can find the Bernoulli's. You can derive the Bernoulli's, right? So using these two equations, we can actually play with this a little bit, and you eventually get to these two equations for the speed of sound.
What was the relationship between the speed of sound and Mach again?
That's how we define Mach number, right? Mach number is a dimensionless parameter that is the ratio of your velocity
Okay, that's
with the speed of sound, right?
picking up whenever you ask me that.
That's
Okay.
Mach number. It's either MA or M. That does. I usually use. I use both of them depending on my mood, but
Okay.
that's true though. Okay. Any questions so far? Yes.
What is U here again?
U is the velocity.
Okay.
U is the velocity, but since it is, So for velocity, we usually use v, right, the capital V. But since it's a one-dimensional velocity, we are going to use this component of velocity,
Gotcha.
which is u, right? Okay. It is already 3:32. Should we continue or should we stop here?
We need to, it feels like a natural place. Got to one of Euler's many annoying equations.
Okay.
All the
That's-
time.
Everything ends or begins with that.
What's that?
Everything ends or begins with that.
With Euler? Yeah, I agree. I
I
agree.
had no life.
Even structures.
Yeah.
Yeah. So an engineer needs to know Euler.
He gets overshadowed by Bernoulli anyway, so.
What's that?
He gets overshadowed by Bernoulli anyway, so.
Euler?
Yeah. No?
No, I mean, there is no Bernoulli in buckling, but there is an Euler in buckling, right?
That is true. That's
There is
true.
no Bernoulli in mathematics, but there are a lot of Eulers in mathematics. Right?
How about that one?
Okay, so let's stop here.